Gnanam paramam dheyam. Knowledge is supreme.
We are going to talk about wave functions as bases. See, so far we have been using x, y, z and so on and so forth as the basis, but the reason why we study it is that we want to work with wave functions. Before we start talking about wave functions as basis, I will briefly draw your notice to two special character tables, or rather character tables of two very special symmetry point groups. One is d infinity h, the other is c infinity v. Okay. Think of H2 for example. So far before we started this discussion on symmetry, we have restricted ourselves to diatomic molecules, right. So the simplest diatomic molecule you can think of is HH, dihydrogen, isn't it, right. Let us see what are the elements of symmetry or operations of symmetry that are there in this dihydrogen molecule. First of all, you have an axis, of course. This is an axis, okay. Cn, what is n here? Infinity. What does that mean? If you rotate by a very small amount, like 0.000000000, as many zeros as you think, 1 degrees, then also you get a symmetry operation, right. This is my dihydrogen molecule. I rotate by any amount, small amount or large amount, does not matter. I get back the same dihydrogen molecule in the same configuration. So this here is Cn. Do not forget, rotation is by 180 degrees by n. So if I rotate by a very small amount, then n goes up. If I rotate by an infinitesimal amount, n is infinity. Are we clear with that? Now, is there any other axis of symmetry? If I go through the midpoint and I draw a perpendicular line, I get a C2, right. Dihydrogen, rotate by 180 degrees, the two hydrogen atoms change places. Now, since my rotation is restricted, it is better to use this pen. This pen is not really like dihydrogen, it is more like HCl, but assume that it is dihydrogen. This is a C2 axis, right. How many such C2 axes can I think? First of all, the C2 axis is perpendicular to the Cn axis, isn't it, C infinity. How many such C2 axes are there? Infinite. This is a C2, this is a C2, anywhere you can have a C2. So there are actually infinite number of C2s. What is the name then from these two? N is infinity and you have perpendicular C2s. So the name becomes D infinity already. Next thing to look for is a horizontal plane. Do I have a horizontal plane here? Where is it? This or this? This is a horizontal plane, right? This here is your sigma h. So this is a D infinity h point group. Which other symmetry operations are there? Inversion, point of inversion is there, right? The sigma v's will be there, okay, many things, okay. So then how do you write the character table for such a an infinite point group? See, H2 is the simplest molecule that we can think of, but its character table turns out to be as complex as it can be, maybe not all that complex also. So the only way in which you can work out this character table is by inspection, right. So these are the irreducible representations. This dot 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 means there are many more, okay. Since there are infinite number of symmetry operations, we cannot of course write them. So what we do is we only write a representative few, E 2C infinity. Why have I written 2C infinity? Where is the other C infinity? C infinity plus, C infinity minus, right. I can rotate this way or I can rotate this way. Then infinite number of sigma v's. I, there is only one. S infinity is also there. C infinity doubles as S infinity. Two S infinities and infinite number of C2s. C2 dash means C2 that is perpendicular to your C infinity axis. And you can work out these characters by inspection. What is this phi? Phi means the small angle or maybe not small angle by which the rotation is performed with respect to your C infinity. Okay. So, this here is the character table for D infinity H, and since it is a special character table, Mulliken nomenclature is also special. See, the first one, first irreducible representation you have, that is of course totally symmetric. So, you would usually call it A1G, but you do not. To recognize the fact that it is a special character table, you call it sigma G plus. This one is A2G. A2G means what? Symmetric with respect to C infinity, therefore A, antisymmetric with respect to sigma V, therefore 2, and symmetric with respect to I, therefore G. Okay? Do not call it A2G, you call it sigma G minus. G is the same, it is just that instead of A1 I am writing sigma plus, instead of A2 I am writing sigma minus. Okay? And then next we come to the two dimensional representation. This one 2 here, 2 cos phi means it is still kind of symmetric with respect to the rotation, and it is symmetric with respect to I. How do you get 2 character? 1 and 1 along the diagonal. So, x remains x, y remains y, that kind of a situation. So, it is E1G, instead of that you call it pi G. Instead of E2G you call it delta G. So, it is important to remember that pi G and delta G or pi U and delta U for that matter are actually two dimensional representations. Instead of E3G you write phi G, and then for all these you have the corresponding Ungerede representations as well. Have we understood, at least roughly, how this character table is written and how the Mulliken nomenclature is performed? Okay. First of all, the character table is worked out not fully, only partially by inspection. Secondly, Mulliken nomenclature is sort of special. Okay. And this is a good character table to start our discussion of your functions, orbitals as basis elements. Okay. Let us see. We are talking about H2, aren't we? D infinity H is H2. So, do you remember the molecular orbitals that we have all studied somewhere or the other, right? What is the lowest energy molecular orbital? 1s is atomic orbital. Okay. Some sigma orbital, right? What does it look like? This 1s plus 1s, right? Actually, it is okay if I simply write this. I do not really have to draw an ellipsoid or something like that, but it is important that I write the signs of the wave function. This is your bonding orbital, and neglect the size, sizes are supposed to be the same, it is just different levels of enthusiasm while drawing the wave function. 1 is plus, 1 is minus. Okay. Now take this, can you tell me to which symmetry species it belongs? The bonding orbital? Let us see. With respect to E, of course, it is the character is 1. With respect to C infinity, character is 1 or minus 1. The bonding orbital, character is 1. With respect to sigma V, is the character plus 1 or minus 1? Plus 1. With respect to I, plus 1. S infinity, C2. That everything is plus 1, right? So, it belongs here, sigma G plus, right? So, what I do is I call it the sigma G plus orbital. What do you call this kind of a bonding? Sigma bonding, isn't it? You call it, this orbital is a sigma bonding molecular orbital. This is why. This is where the name comes from. This well known sigma name comes actually from the character table. That is why you call it sigma. Okay. So, this orbital will now, from now on we are going to call it sigma g plus orbital. You might note that I have used small sigma here, right. That is the other convention we are going to follow. Whenever we write a wave function, we will use small letter. Whenever we talk about a state, we use a capital letter. That is going to come very handy in our discussion of electronic spectroscopy. Okay. That being said, where does this belong? The antibonding orbital, antibonding orbital. What is the character for E? -1, 1. What is the character for C infinity? 1 or -1? Not -1, be careful. 1, confident, 1, okay, then it is 1. What is the character for sigma V? Where is sigma V? Sigma V, this is your C infinity, right. So, do not forget horizontal plane is like this and sigma V is the plane of the board. So, let us try again. What is the character for sigma V? +1. See this plus and minus, right. So, you can think of them as spheres, okay. I am basically bisecting a sphere. This plus you can think is a red sphere, minus you can think is a blue sphere. But red and red interchange, red and red hemispheres, blue and blue hemispheres interchange. Are we clear? So, that is -1, remember. So, now 1, 1, -1, what about I? Symmetric or antisymmetric with respect to inversion? We are talking about the bonding orbital, sorry, antibonding orbital. Symmetric or antisymmetric? Antisymmetric, convinced? Are we convinced? Start from any point, go to the center, extrapolate, the sign changes. So, -1. What do we have? 1, 1, -1, -1. S infinity? S infinity? Rotation and then reflection. So, the lobes interchange, okay, -1. C2 dash, C2 dash, C2 dash, exactly, Tader. Do not forget this is C2, right. So, you do a C2 dash, plus and minus lobes interchange, okay. Plus minus, where is C2? Here. So, interchange like this. Okay, so what are the characters? 1, 1, -1, -1, -1 everywhere else. Where is it? Where is it? Oh, then it must be somewhere here, right? First of all, it has to be U, A1U. A1U is something we do not use, we use sigma U plus. Yes, sir. Sorry. Sigma V is +1, not -1. Did I say -1? I made a mistake. Do not forget what sigma V is. Actually, we discussed it correctly, but then in the heat of the moment I changed the sign. This is sigma V, right, plane of the board. So, as you agreed, for sigma V the character is +1, not -1. So, I made a mistake here. So, character of E is 1, character of C infinity is 1, sigma V is 1, I -1, S infinity -1, C2 dash is -1, okay. So, this orbital is called the sigma U plus orbital. If you want to add a star to denote that it is antibonding, it is up to you. Are we clear? Are we clear? So, what we have demonstrated is that at least molecular orbitals, wave functions of a molecule, electronic wave functions of a molecule can form bases for the irreducible representations. and that is what forms the basis of symmetry classifications of wave functions. Okay. Let us close today's discussion with this D6H. No, not D6H. Actually, I want to do octahedron. Okay. For the moment, I do not want to show you the last column. Okay. Let us talk about the atomic orbitals of the central metal ion in an octahedral complex. Okay. S orbital of course is totally symmetric, right, a sphere. Now, it is important to understand that a sphere is the most symmetric object you can think of, right. It has infinite number of symmetry operations of infinite kind. Only one symmetry operation is there, which is only 1 in number for a sphere, that is the point of inversion. Otherwise, you think of any line that goes through the center, it is Cn, and n can range from anywhere to anywhere, right. There are infinite such. You can think of infinite planes going through the center and so on and so forth, right. So, well, if you think of the s orbital, any s orbital of the central metal ion in an octahedral complex, it will be A1G, right. Think of the p orbitals. P orbitals are along x, y, z axis, right. Where will they belong? Same symmetry species, same irreducible representations as your x, y and z, and here as you see x, y, z jointly form the basis for T1U. So, for an octahedral complex, S is A1G, P x, P y, P z jointly form the basis for T1U. What about the d orbitals? Do you remember the names of the d orbitals? dz square, dxy, dyz, dzx. So, these are all your quadratic functions, isn't it? And can you tell me why dz square is called dz square or dzxz, zx is called dzx? Because in these wave functions, those functions are actually there. There is something like 3 cos square theta by r square minus 1 in dz square, okay, and that when equated to 0 gives you the equation of the node. Maybe what we will do is we will stop here and we will start from here next day and go on to vibrational wave functions. First we will talk about the d orbitals, then only we will go on to vibrational wave functions.